All right, so I wanted to do a rundown of what I think is a pretty difficult multi-step synthesis problem with alkynes. So we are beginning with the acetylide molecule here, and we are ending up with something that doesn't resemble it in the slightest, this crazy looking alcohol. We have this carbon chain over here, we have this cyclohexane over here. So how do we even approach this? Well, we know, for one, we are breaking our alkyne completely. This is an alkane on the right. We're breaking all of our pi bonds. We're adding an alcohol, and we're certainly adding a bunch of carbons. Those are the three things that we need to look for here as we're looking for reagents for this. Whenever you're given an acetylide, you're kind of being given a gift. You know that you can deprotonate this, put a negative charge on a carbon, and really add whatever you want. It's a very easy way to extend a carbon skeleton, okay? In order to do that, we're gonna use NaNH2, which is going to deprotonate one of the carbons, all right? That allows us to add in anything attached to a Br or a Cl, all right? So we're gonna add 2 carbons to our acetylide. Why am I choosing 2 carbons? Well, I'm kind of cutting this in 2, all right? This is the 2 carbons that I'm gonna add. And these are the carbons that are in the acetylide compound. And what I'm basically doing is cutting this whole thing in half and saying, this is going to be this is my starting reactant. I'm adding 2 carbons over here, and I'm adding this ring and this alcohol over here, all right? Now, how did I figure out how to do that? Well, honestly, through a lot of trial and error. But we know that we can add to 2 sides of this. So why not try to find a great area here that we could add 2 things to, all right? So we're gonna add this part first, and that's exactly what we do, and that's what we have in this step here. We have where those 2 carbons are going to be, which is there, and then the 2 additional carbons. So in essence, the entire right side of our molecule is complete. So now we have to figure out, well, how are we going to add a ring with an alcohol to it, okay? Now, it was initially thought that you could just add this and put a bromine on the end of it and just connect it to your terminal alkyne. Now, I don't know if that would work for this. It's not the solution we're looking for here though, okay? The clue that we were given for this is that it includes either an aldehyde or a ketone as an electrophile. So we're using either an aldehyde or a ketone as an electrophile. So that was our clue. So we're gonna use actually kind of a funky looking, this is a ketone. It's a carbonyl functional group connected to a carbon that is then connected to 2 other carbons. And what's gonna happen here is actually pretty interesting. I think I did skip a step here, I'm sorry. When we got to this step here, we added our 2 carbons. We wanna work with this side too, so we added to one side, we wanna add to this side. So we are going to bring in another NaNH2 to then deprotonate this, so we know we can add something to this compound. We also know that this is a nucleophile. Carbon has electrons to share. Carbon has electrons to share. It has a negative charge, so we need an electrophile to react with this, okay? So enter this ketone. What's gonna happen with this ketone? There's a bit of a mechanism involved here. Don't forget that oxygen is electronegative, carbon is relatively electropositive. So there is going to be a little dipole here. There is going to be a little electronegative difference. And we have a partial positive charge here, which is what is going to make this a suitable electrophile. So we're gonna draw an arrow from our lone pair to our partial positive charge electrophile here. That is then going to kick the pi electrons onto oxygen. Oxygen loves pulling electrons from a pi bond. You're gonna see that so often in this class, especially with acids and bases. And anytime that we draw an arrow from a lone pair to anything, the entire molecule is going to come with it, okay? There's a bit of an intermediate step here. After this ketone goes through all these electron movements, we end up with something that looks like this. So we can see that this was this kind of bond that was created from the negative charge that was on this side and the positive charge that was on this side, okay? Make sure that's very clear. You wanna make sure that you're counting your carbons for everything. So this is just this beautiful marriage between an electrophile and a nucleophile. Now, because we did correct this positive charge, so these are not actual charges, I did just wanna show you why this bond was created. However, oxygen is still gonna retain a negative charge because we brought up some extra electrons. It starts with a valence number of 6, 5, 4, 3, 2, 1, 0, -1. That's why there's a negative charge here. So this is our kind of intermediate step here. So before we continue, and we know that we're getting pretty close to the answer here. So you can see the answer up there. We're getting kind of close. We know we need to break this alkyne twice, but we also need to kind of fix this. So this is kind of one of those odd steps. It's just gonna be a workup. It's either H2O or I think it's like H2O and hydrogen, but there's a workup there. All that's simply gonna do is protonate that oxygen, all right? We're gonna neutralize that charge. We're gonna make that a hydroxyl group. So now we are looking very similar to our final product, which is down here. Simply, all we have to do to get from there to there is get rid of these pi bonds. How do we do that with an alkyne? Simple hydrogenation, all right? We're not using Lindlar's. We're not using NaNH3, I believe. We're not worried about like cis alkenes or anything. We're going all the way to an alkane, so we can do normal garden variety hydrogenation with the palladium catalyst that breaks all of the triple bonds, and that comes up with our answer. You always want to double check and count your carbons so we know that we have 1, 2, 3, 4 carbons coming off. This is our original compound that we were trying to get to. 1, 2, 3, 4, perfect. The OH is on kind of that upper right corner of our ring. There we go. Make sure that we drew a hexane and we did 1, 2, 3, 4, 5, 6. So all the carbons are accounted for. And that is the solution, or one solution. I believe that there are actually a couple different ones, but this is the one that we were looking for here. So there you have it.